Hello. Yeah, very good morning to one and all. So, for I am very glad to introduce today's session speaker, Dr.M. Narendra Kumar, currently working as professor at Center for Incubation, Innovation, Research and Consultancy, CIARC, Jyoti Institute of Technology, Bangalore. He obtained his bachelor degree in mechanical engineering from Bangalore University, master's from Pondicherry University, and doctoral degree in heat transfer and CFD domain from Vishwesvaraya Technological University. He has qualified GATE and has 19 years of teaching experience at graduate and 10 years of teaching experience at postgraduate levels of engineering. He has guided more than 25 projects at graduate and 15 projects at postgraduate level. He has more than 12 research papers to his credit in international conference and referred journals, and has participated in more than 15 workshops. His areas of interest include heat transfer, thermodynamics, computational fluid dynamics, refrigeration and air conditioning, turbo machines, and IC engines. He has the honors of life member of ISTE and MIE. Presently, he is working on a funded project from ISRO, SAC, Ahmedabad on heat transfer application. And to his credit, he has worked under many funded projects. So now I hand over the session to Dr. M. Narendra Kumar.
Good morning.
Good morning, sir.
So good morning, sir. Is the screen visible?
You can, sir. You can start, sir.
Yes, sir. Is the screen visible, sir?
Screen is not visible, sir.
Yeah.
Yes, sir. Visible, sir.
Visible,
Yes,
sir.
Okay, so today I'll be trying to present an introduction to CFD. So we'll try to look into what exactly is CFD. So the outline of today's presentation will be, we'll be looking at what exactly is CFD, why we need CFD, and where CFD is used. And we'll look into the architecture of the CFD, so mean to say how exactly the CFD works, and what are all the problems with CFD. We'll be looking at it, and we'll be looking at certain available CFD codes, and for quite a few case studies that we have undertaken. So basically, we would like to know what exactly is CFD. So CFD stands for Computational Fluid Dynamics. Okay, it's not colorful diagrams, it is Computational Fluid Dynamics. So we'll try to look into what exactly is Computational Fluid Dynamics, so shortly called as CFD. So you can come out with different definitions of it. So probably CFD is the analysis of system of equations involving fluid flow, heat transfer, and associated phenomena such as chemical by means of computer-based simulations. Okay, so we use computer-based simulations. The technique is very powerful and spans over a wide range of industrial and non-industrial applications. Okay, so this is how you can define the CFD. Okay, so basically, whenever you come across the CFD, it involves a simulation using the high-end computers. Okay, so this is how we try to define CFD. So now why CFD, we'll look into it. Basically, whenever you try to analyze a problem, you come across three approaches. One is analytical fluid dynamics. The other one is experimental fluid dynamics and computational fluid dynamics. So whenever we come across the analytical fluid dynamics, which essentially is called as the analytical methods, so the analytical fluid dynamics is restricted due to the linearity. Okay, so whenever you come across a problem in nature, so the problems are usually complex and non-linear. So the analytical the analytical methods will be in a position to solve only the linear problems. So we cannot tackle the non-linear problems of the physics. So the analytical fluid dynamics restricted to linearity. Essentially, when you come across experimental fluid dynamics, okay, so experimentation is it the cost, time, everything is involved in it. So the experimentation is too costly, and also it is restricted due to the modeling issues. Okay, so we have to look into the modeling issues there. So it is restricted by the modeling issues, cost, and the time that is involved in it. So the third approach we called as the computational fluid dynamics. Okay, so we'll look into it. Why CFD here? So it is used in the analysis and design. So simulation based design instead of building and testing. So more cost effective and more rapid than EFD. EFD refers to experimental fluid dynamics. So CFD provides high fidelity database for diagnosing fluid flow problems. So simulation of physical phenomena that are difficult for experiments. As I told you, you have scaling issues when you come across experimentation. So whereas when you come across computational fluid, it is very easy to model it. Okay, so full scale simulations, environmental effects, hazards, physics, and also it is used for the knowledge and exploration of the physics. So now we look into where exactly CFD used. So CFD is nowadays used in every field of engineering. So I'll try to list out quite a few here. So the first application of the CFD, you can find it in aerospace. Okay, so for analyzing the flow over an aircraft, so many things are involved in it. Okay, so aerospace, you can look into it. The second application, you can look into the automotive segment. So here again, so you find the application even in the combustion of the IC engines, all those. So the next application I will be looking at it, the biomedicals. Okay, so you can see the flow of blood through the arts, and you come across the aortic hemodynamics. Okay, so these are just quite a few applications in biochemical, biomedical applications. So next we come across certain chemical processing applications. So even the chemical reactions can be modeled using CFD nowadays. Okay, so these are quite a few applications of chemical processing that you can see. Next is HVAC. Okay, so you can find its application in HVAC. So then you come across hydraulic system. So it is used for modeling the hydrodynamics. So hydroflow. So then you come across the applications even in marine. So you can model and try to carry out the CFD analysis. So then you come across the application in oil and gas flow. Okay, so which is used for simulating it. So then you come across the power generation. Okay, so where you can use the CFD even in the power generation aspect. So then you can use it even in the sports. Okay, so the sports. So these are all quite a few applications that I have listed it here. So very limited applications I have listed. As I told you, it can be used in wide applications of engineering fields, not necessarily these. Okay, so now we look into it, how exactly a CFD works. Okay, so CFD codes are structured around a numerical algorithm that can tackle fluid flow problems. In order to provide an easy access to the solving, all commercial codes or include sophisticated user interface. So whenever you come across any commercial codes, so it has been divided into three categories. So pre-processor, processor, and post-processor. Okay, so we'll look into what exactly the content of a pre-processor, processor, and the post-processor. Okay, so all commercial codes include pre-processor, processor, and post-processor. So now we look into the pre-processing aspects of the CFD. Okay, so the first aspect of the pre-processing is we need to define a geometry. So geometry is nothing but a computational domain. Okay, so whenever you try to model a certain aspect for the CFD analysis, the geometric model is essential. So you mean to say you need to create a geometric model or a computational domain in order to analyze it. So the next aspect is the grid generation. Mean to say the defined computational domains will be divided into number of smaller subdivisions, which are essentially called as grid generation or meshing. Okay, so we'll be trying to divide the computational domain into smaller subdivisions. Okay, so subdivision, this is the second aspect. So the next aspect is the selection of the physical and chemical phenomena that need to be modeled. Okay, so we'll be trying to select the physical and chemical phenomena that need to be modeled. So then you come across the definition of the fluid properties. So what is the type of fluid that you are trying to use it? Based on the type of fluid that you are using it, you need to define the fluid properties accordingly. So then once after defining the fluid properties, the next aspect is to define the appropriate boundary conditions. Okay, so the appropriate boundary conditions are essential. Without the boundary conditions, you cannot arrive at the solution of the problem. Okay, so the more appropriate boundary conditions are essential in whenever you come across the analysis of a CFD problem. So boundary conditions are very much essential and you need to define it accordingly. So these are all the content of the preprocessor. So first one is define the geometry. Next is grid generation, the domain into number of smaller grids, smaller overlapping subdomains. Next is the trying to define the physics. Okay, so and conditions. When you come across a fluid flow boundary conditions, you come across many boundary conditions. Okay, so many boundary conditions like non-slip boundary condition, velocity inlet, pressure. Okay, so like this you come across it. So you need to select the appropriate boundary conditions and try to define accordingly based on the type of analysis that you are trying to work it out. Okay, so these are all the contents of the preprocessor. So once after dealing with the pre-processing aspect of the CFD, next we'll be looking at the solver or the processor. Okay, so probably, so here, so whenever you come across the solver or the processor, so the approximation of the unknown flow variable by means of simple function. Okay, so you need to approximate
Hello, Narendra Kumar sir. Tulsidas.
ಬರ್ತಾರೆ sir.
Voice break.
ನೆಟ್ವರ್ಕ್ ಏನೋ ಪ್ರಾಬ್ಲಮ್ ಇದೆ.
Maybe some technical.
We shall wait.
Voice break ಆಗ್ತಾ ಇದೆ. Okay sir, right.
ಸೊ ಈಗ ಕಾಣಿಸ್ತದೆ ಸರ್? ಹಾಂ ಸರ್, ನೆಟ್ವರ್ಕ್ ಇಶ್ಯೂ ಇತ್ತು ಅನ್ಸುತ್ತೆ. ಹಾಂ ಸರ್, ಹಾಂ ಈಗ ಕಾಣ್ತಾ ಇದೆಯಾ ಸರ್? ಓಕೆ ಸರ್. ಸೊ ಪ್ರಾಬ್ಲಿ ತಿರ್ಗಾ ಕಂಟಿನ್ಯೂ ಫಸ್ಟಿಂದ ಮಾಡಬೇಕಾಗತ್ತಾ ಹಿಂಗೆ? ಓಕೆ ಓಕೆ ಫೈನ್ ಸರ್. Okay, so once after dealing with the pre-processing, so we'll be looking at the solver or the processor. So whenever you come across the solver, so the first and important aspect in the solver is to approximate the unknown flow variable by means of simple function. So whenever you try to approximate an unknown flow variable, yes? Hello?
ಸರ್ ಸ್ಕ್ರೀನ್ ಕಾಣಿಸ್ತಾನೆ.
ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗಿದೆ ಬಟ್ ಇವಾಗ ಬಂತು ಸರ್.
Yeah. Oh, fine.
ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಿ ಸರ್.
ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡ್ಬಿಡಿ ಸರ್.
Yeah.
Yes sir.
Yes.
Yes sir.
Okay, so
Okay sir.
yes. So now we'll be dealing with the solver or the processor. So whenever you come across the processor or the solver, so the first aspect is to approximate an unknown flow variable by means of simple functions. When we try to approximate the flow variable by a simple function, basically you come across three methods. The first one is finite difference method, the second one is finite element method, and the third one is finite volume method. So probably look into these methods in the later stages. So the second aspect is to discretize or discretization of the governing equation by subsequent mathematical manipulations. So whenever you come across the fluid flow and heat transfer, basically you come across three essential equations. One is the conservation of mass, which yields mass conservation equation or continuity equation. So conservation of momentum, you come across momentum equation. Basically you can call it as Navier-Stokes equation also. Okay, Navier-Stokes equation or momentum equation. And the third one is conservation of energy, where you get the energy equation. So basically whenever you try to tackle a fluid flow and heat transfer problems, so these are all the basic governing equations that you come across it: conservation of mass, conservation of momentum, and conservation of energy. So whenever you come across these equations, so in the CFD you try to replace these governing equations or the partial differential equations with the approximate finite difference or finite element or finite volume equations. Okay, so you try to replace the derivatives of the governing equation with the approximate finite difference or finite element or finite volume approximations. So once after you replace the governing equation is the approximations, then you need to convert these equations into the algebraic equations. So once the algebraic equations are converted, so you can solve the algebraic equations using any numerical techniques. So basically you can use the direct method or indirect method based on the need and try to arrive at the solution of the problem. Okay, so these are all the content of the solver that you come across it. So we'll look into a bit on what exactly you try to do it in a finite difference method. So when you come across a finite difference method, so we need try to describe the unknown flow variable of the fluid medium at the grid point or the node point. Okay, so you try to arrive at the solutions only at the grid points. The solution is not continuous, it is only discrete whenever you come across the CFD or approximate solution techniques. So then you try to replace the partial differential equations with the finite difference equations. So the finite difference equations are obtained using the Taylor series. Okay, so when you try to truncate all the higher order series in the Taylor series, you can try to arrive at the different finite difference approximation like forward, backward, first order, second order. So these are all the different equations, finite difference equations that you come across it. So based on the need of the governing equation, you can replace the partial differential derivatives of the governing equations with suitable finite difference equations. So once after trying to replace the partial differential equations with the finite difference equation, so next is replace it by a finite difference equation, and then convert these finite difference equation into the algebraic equations for the unknown variable. Okay, so once after converting into the algebraic equations, so you can use any of the numerical technique to arrive at the solutions of the finite algebraic equations. So this is what basically happens in your finite difference method. So next, when you come across finite element method, so here we try to use the piecewise function. Okay, so piecewise function of an element to describe the local variation of unknown flow variable. Either it can be linear or quadratic or polynomial variation. So the approximation function is substituted in the equation and then try to reduce the error. Okay, so reduce the error or the residual by minimizing by using the weighted functions. So once after working out the weighted functions of it, then you need to convert these equations into the algebraic equations. Once after converting to algebraic equations, so you can arrive at the solution of the algebraic equation using the approximating functions. Okay, so next we come across the finite volume method. So basically all the commercial packages use finite volume method. Okay, so whenever we come across the finite volume method, the first aspect here is to integrate the governing equation. Okay, so we try to integrate the governing equation of the fluid flow over the control volume. Okay, so first aspect when you come across finite volume is to integrate the governing equation. Once after integrating the governing equation, next is the discretization. Mean to say you try to replace the partial differential equation with the finite difference equations of the integrated equation. Okay, so you try to replace the partial differential equations with the finite difference equation or the finite difference approximation of the integrated equation representing the fluid flow. So then we need to convert all this partial differential the finite difference equation into the algebraic equations. So once after converting the finite difference equations into the algebraic equations, so you can arrive at the solutions of it. So next we look into the different numerical techniques that are used for the solution. Okay, so there are different numerical techniques like tri-diagonal, pentadiagonal. So these are the different solvers that are being used. Okay, so whenever you come across the solvers, these are all the advanced solvers that you come across it. So there are direct and indirect methods. So when it is a direct method, you use Clammer's rule, Gauss elimination, or LU decomposition. So these are all the techniques that are used for solving the algebraic system of algebraic equations. So whenever you come across the iterative method, you try to use the Jacobi method, Gauss-Seidel, and SOR method. These are all the different iterative methods that are being used. Okay, so to solve. So whenever you come across the unsteady problems, so you try to use the different in order to take care of the time derivative. So you come across explicit Euler method, implicit method. These are all different techniques that are used. So whenever you come across the numerical analysis or the numerical methods, so the following methods are controlled or need to be used in the calculations. So under relaxation factor, you need to set the convergence limit. So different numerical schemes. So monitor the residuals. So number of iterations for the steady flow or the number of time steps that are needed for the unsteady flow problems. Whether we have to go with the single precision or double precisions. So these are all the things that you are supposed to look into it. Okay, so this is about the solver or the processor that you come across it. So next is the post-processing or post-processor. So where once after arriving at the solutions, basically the post-processor are used for visualization of the results. Okay, so basically post-processor is used for visualization of the results. So whenever you come across the visualization of the results, so you try to go for the grid display, geometry display, you try to plot vector plots, line and color contour plots, 2D and 3D plots. So you can also look into the particle tracking of it. View manipulations can be done. So color postscripts, outputs, these are all the things that can be worked out using the post processor. Much more things can be done beyond this also when you come across the post processing. Okay, so this is next you come across certain aspect or the problems involved with CFD. So whenever we come across the CFD, so need to be aware that the underlying physics and the results generated by the CFD code are best as good as the physics. Okay, so prior to setting up the CFD simulation, so the stage for identification and formulation of the fluid problem is in terms of the physical and chemical phenomena are to be considered. So I mean to say, so you need to be well aware of the physics of the problem before getting into the CFD analysis of the problem. So let me consider airflow in a room for a CFD analysis. So before getting into the CFD analysis, first of all, we need to look into the physics of the problem. Okay, so now we can try to analyze the airflow in a room. So you need to make certain assumptions. So when I try to consider the airflow in a room, so first and the foremost thing is I need to look into whether the flow is laminar or turbulent. So these are all the physics that you need to consider in. So the first and aspect is whether the airflow in a room is laminar or turbulent. So based on that, you need to try to use the equations accordingly. So then you know that air is compressible in nature. But if the Mach number is less than 0.3, you can treat it as incompressible. So can I treat air as an incompressible flow? Okay, so you need, this is the second aspect that you need to look into. So whether I need to model it in 2D or 3D. Okay, so whether I need to go for a 3D analysis or a 2D analysis. With the aid of 2D, can I capture much of the physics? So these are the things that you need to consider it. Okay, so there are many aspects that you need to consider it. So whenever you come across a CFD analysis, because the physics of the problem is very, very important. Okay, so the physics you need to understand, then convert that into mathematics. Okay, so then you need to convert the physics into mathematics, which is nothing but you try to input everything into the CFD analysis. Okay, so the main aspect here is the physics of the problem is very, very important, and you need to have a very good knowledge on the physics of the problem that you are trying to analyze it. Okay, so once if you are very good at physics, so whenever you come across a CFD analysis, so you need to make the problem as simple as possible with suitable approximations. Okay, so that is one of the important aspect when you come across a CFD analysis. Okay, to a greater extent, we need to simplify the problem. Okay, so when you come across the CFD analysis, in addition to that, good understanding of the numerical solution algorithm is also very, very important. So mean to say, you need to try to understand what exactly is convergence, consistency, and stability. Okay, so probably you come across because these are all approximate solution techniques. Are you getting that? Okay, so and one more thing you have to look into it, the grid independency study also. Okay, so grid independency study is also very, very important when you come across the CFD analysis, because the solution should not depend on the grid size. Okay, so you come across even that is very, very critical when you come across the CFD analysis. Okay, so when you come across the convergence, the numerical method to produce a solution should approach the exact solution as the grid size reduces to 0. Okay, so this is what we call as the convergence. So next, when you come across the consistency, a consistent numerical scheme should produce a system of algebraic equation which can demonstrate to be equivalent to the original governing equation as the grid size reduces to 0. Okay, so next when we come across the stability. So stability to do with the errors that are involved in the numerical methods. Okay, so the simple example that I give you is the round-off error. Okay, so the round-off error. Okay, so as the simulation proceeds, the round-off error should reduce. If the round-off error does not reduce or grows with the time step or the iteration, so divergence will be detected in the solution. Okay, so this is one of the examples that I can give it for the stability. Okay, so these are all the different issues concerning with the CFD. So probably if you can come across, there are quite a few available codes. When you come across the commercial codes, there are plenty of commercial codes. Basically, all those commercial codes uses finite volume method. Okay, so finite volume method is being used in all these commercial codes. So Fluent, Star CD. Okay, so you come across CFX, Cosmo. These are all the different CFD, commercial CFD packages that are available. Okay, so the customized packages are also available now. Then you come across certain research codes, and you come across certain public domain codes, and these are the information that you come across it. Okay, so CFD online, you can get much stuff pertaining to the CFD analysis using the CFD online. And there are there are certain public domain codes that are available. So where you can use those codes and try to modify it. Okay, so you come across CFD software, grid generation software are available, flow visualization software are also available. Okay, so this is about the available CFD codes that you come across. So now we'll look into quite a few case studies. Okay, so this was the DST project that we undertook. So was the development of 1 kilowatt redox flow battery. Okay, so the objective here is, so this is a redox flow battery which I have shown it here. Okay, so this is the anode and this is the cathode, mean to say the positively charged electrolyte and the negatively charged electrolyte. So you come across the flow domain. So you come across the porous media or the electrode and a membrane here. Okay, so basically here we try to carry out the CFD analysis to look into the hydrodynamics of the fluid. Mean to say the basic idea was here to select the appropriate flow channel, so where the pressure losses are minimized. Okay, so still more is there. So the chemical aspect we are still working on it. Okay, so these are all quite a few flow channels that we try to design it. Okay, so this one is the serpentine flow channel, so which we try to design. So a single serpentine flow channel. So this is the velocity contours and this is the pressure contour. Okay, so that you come across it for a single channel serpentine flow field, and this is the interdigitated flow field which we try to work it out, and this is the velocity contours and the pressure contour. Similarly, we try to work on even the parallel flow field. Okay, so the parallel flow field, and this is the pin type flow field that we had worked on it. Okay, in addition to that, we have also worked on the multi-serpentine flow field, because the multi-channels can be worked out only with the serpentine flow field. So we try to work out even the multi-serpentine flow field. Okay, so this is a square multi-channel serpentine flow field, and this is a rectangular serpentine flow field. So the basic idea behind this hydrodynamic analysis was to look into the pressure drop. Okay, so basic idea here was to select the channel which was giving the least pressure drop. Okay, so least pressure drop and wettability. Okay, so wettability. So this is one of the case study that we took it. So the second case study was to develop the CFD code. Okay, so whereas when we came across this, we used the commercial code in order to solve the problem. So whereas here for this particular case study, we had developed the code. Okay, so we have developed the code using the Fortran. Okay, so language. So this is the physics of the problem that is given. So this is the rotating enclosure that we have it. So the air is filled in it. Okay, so the air is filled in it, and this is the rotating enclosure that you come across it. And this end, okay, so this side of the rotating enclosure was subjected to constant higher temperature, whereas this, okay, so side of the enclosure was subjected to constant temperature or sink temperature. Okay, so this was the temperature at this surface was higher than this particular surface, and these two, okay, so surfaces or the wall of the enclosure was treated adiabatic. I mean, this is a rotating enclosure. Okay, it's a slow speed rotating enclosure that we have it. Okay, so this is the physics of the problem. So where we try to develop the code, so we have arrived at the mathematical expressions for the physics of this problem. So I have tried to arrive at the rotating frame. Okay, so this is the mass conservation equation that you come across it, and it's two-dimensional nature. So because the variation along the three-dimensional was minimum, because third direction, so the z direction was not much, because the tube was too long. So hence we try to work out on a two-dimension, so variation. So this is the X momentum equation that you come across in the rotating reference frame. Okay, so this is the thermal buoyancy that you come across it, and these are all the Coriolis forces that you come across it. Okay, so this is the X momentum equation, and this is the Y momentum equation in the rotating frame, and this is the energy equation that you come across it. So next the aspect is, so whenever you try to develop a code, we try to non-dimensionalize the equation in order to study the effect of the different non-dimensional parameters. That is one of the greatest advantage whenever you try to develop a code. Okay, so develop a code. So you try to develop the code in terms of the non-dimensional parameters, because you can study the effect of each and every non-dimensional parameter. So that is the greatest advantage whenever you try to develop the code. Okay, so these are the different non-dimensional variables that we have used it. Okay, so using this different non-dimensional numbers, okay, so are the non-dimensional numbers, we have tried to non-dimensionalize the equation. So when you try to non-dimensionalize the equation, so you can see that this is the continuity equation that you get it, and this is the x momentum equation. As I told you, we see that this is the buoyancy term, this is the centrifugal force term, and this is the Coriolis force term that comes into play here. And similarly, this is the x momentum equation that you come across it. So as usual, this is the Coriolis force term, centrifugal force term, and the buoyancy term that you come across it. Okay. So, and this is the energy equation in the non-dimensional form that we try to arrive at. Using these variables, we have non-dimensionalized it. So whenever you try to analyze a problem in CFD, so we need to get all these equations into a generic form of equation. So whenever you try to come across CFD, this is the most generic equation that you try to come across it. So this is the temperature derivative or time derivative that you come across. This is the convective term or the convection term, and this is the diffusive term that you come across it, and this is the source. Okay, so the equations that I have shown it here, all these equations, now I'll be trying to write it in the generic form here, and you can see that based on the equation, so the variable phi, okay, so these are the equations that it takes. Okay, so this is the phi, this is tau, and the lambda, and this is the source that it takes. So based on the mass conservation equation, you can see that, okay, so phi is equal to 1, and lambda is equal to 0, and source equal to 0. So, I try to input these things here. Finally, I'll try to get this equation. Okay, so finally, I'll try to get that equation. Similarly, when you come across the x momentum equation, so we can suitably replace these variables, and you can see that this is the equation that I try to get it. Okay, similarly, with respect to y momentum and energy. Okay, so these are the equations that we have written in the generic transport equation form. Okay. So next, using the finite volume methodology, we have tried to discretize all this differential equations. Okay, so this is the flow chart that we come across it here. Okay, so first aspect when you come across here is to assign the initial values for the velocity and the pressure fluids. Next is to set the boundary conditions, set the time step. Okay, so these are all the initial values of the velocity fields that we have set it, and this is how the calculation that we are. Okay, so we look into the developed code here. Okay, so these are all the different subroutines that we have worked it out. So this is the main program. Okay, so that will try to call all the subroutines. Okay, so it is an unsteady flow problem that we have worked out it. So, okay, so the output I have tried to, and these are all the different equations. So now you can see here, this is the subroutine that I have worked out to initialize all the flow variables. Okay, so to initialize all the variables that I have set here. Okay, so this is the subroutine that I have worked out in order to generate the grid. Okay, so I have gone for the uniform grid here. So you can also go for the non-uniform grids, mean to say fine grid at the wall of the enclosure and porous grid at the middle. So this is the program that you try to work it out. Okay, so I have gone for the uniform grid, or you can work out the non-uniform grid also. So this is the code that we have generated for the generation of the grid. Okay, and this is the code to update the variables at the time step. Okay, so and this is the x momentum equation. Okay, the coefficients and the equations in order to solve. So these are all the things that we have worked out. As I told you, we have used the finite volume methodology. Okay, so this is the code that takes care of the subroutine in order to solve the u momentum equation. Similarly, This is the y direction momentum equation, the code subroutine, and this is the code for the temperature. So in order to solve the temperature, so this is the code that we have used it, and this is the code. Okay, so because you need to couple the pressure and velocities. Okay, so using different ski algorithms. Okay, so I have gone for the simple algorithm here. So using the simple algorithm, we have tried to couple the pressure and velocities. So, and this is the solver that I have used it. I have gone for the tri-diagonal matrix algorithm in order to solve the equation. So this is the solver that we have it, and I have to print all the results in the form. So I try to print the results so that I can use the post processor and try to display the results. So I have tried to write a code to print the variables. So that is compatible with the post processor. So this is the code that we have it. So just I'll try to run the code here. Okay, so this is how the code runs. Okay, so the output you can see here. Okay, so I have tried to get the output. Okay, so this is the output that it will try to display it. Okay, so at each and every point, okay, so it will try to display the temperature at each grid point, the velocity, pressure, x velocity, pressure, and this is nothing but the motion pressure that comes into play because of the enclosure is rotating. Okay, so these are all the values that you try to get, and using these values and using the processor, you can try to work out the solutions or the post-processing operate. Okay, so once after dealing with the post-processing, so probably since we have developed the code, so the validation of the code is essential. So in order to validate the code, we have tried to validate it with the experimental. Okay, so analysis that was carried out by some person. So this is the experimental and this is the simulation result that we have had. So because the enclosure is rotating, so this is for the 0-degree rotation, mean to say at that position. Okay, so you see that this is the higher temperature surface and this is the lower temperature surface. These two are adiabatic walls that you come across it. Okay, so this wall was exposed to higher temperature. You can see the contour here and the variation. So this is the variation that you come across. So you can see this variation and this variation. Okay, it's very similar. So this and this variation, you can see it is very similar. So similarly, at 270-degree rotation, you can see this variation here and this variation, similarly this variation. Okay, so this is the validation that we had carried out. So in addition to the validation of the contours, so we have tried to validate it with the Nusselt number also at the hot wall and cold wall. So you can see these blue color dots are the experimental values and the line, okay, so which is the numerical study that was carried out. Okay, and this is the average Nusselt number variation for different Taylor's number that was carried out. So this dotted line represents the experimentation that was carried out, and this, okay, brown color line is the simulation that we need carried out. So you can see that the results are when very close approximation, hence the validation of the code was taken care of. Okay, so in addition to this, we also carried out one more computational studies. Probably this is the current CFD study and experimentation that we are trying to work it out for one of the funded project. Okay, so wherein we need to develop an heat sink or pulsating heat pipe. Okay, so pulsating heat pipe for the space application. So for which we try to consider the different designs. Okay, so different designs were considered. So these are all the different designs that we try to undertake. Okay, so once after considering the different designs, so then we try to carry out the simulations on it. Okay, so where it is a two-phase force simulation that we are trying to work it out, and these are all the boundary conditions that we try to set it. And this is the processing that we have done it. So probably this is an unsteady simulation that you come across it. Okay, so these are all the simulation results that you try to arrive at it. Okay, so this is one of the case study that we are working on it. Okay, so thank you. So any doubts you have it or any queries? Yes, any queries?
Narendra Kumar, sir.
Yes, sir.
Dr. Mahadev Swami.
Yeah.
Thank you, sir. Here, I have one question, sir, behalf of student and participants.
Yes, sir.
The new learner who is going to learn CFD, they will think that complicated fluid dynamics. It is, yes, name itself shows the complication. So what is your advice for new learner about the CFD? And one more question.
Yes, sir.
If the mechanical student learn CFD as well as the software tools or coding,
Yes,
so
sir.
what is the exclusive opportunities for them?
Sir, essentially, the CFD package is totally a different thing because it's a software that we have it. So basically, it's a black box. If you input something, it will give you some output. But that is not important. So you should have the sound knowledge of the physics and the mathematics. Only when you have the sound knowledge of the physics, you know what exactly you are trying to solve it. Okay, so mean to say, if you don't know the outcome of the solution, if you input something, it will give you some solution. But if you are not in a position to interpret the output of the solution, then things goes wrong. So that is the reason. So the sound physics of the problem is very, very important. Once if you can understand the physics of the problem, then try to make certain approximations. Mean to say, so based on the need of the problem, you need to approximate. Mean to say, whenever you come across CFD, we need to simplify the things. There is nothing like complicating the things. We need to simplify the problem, then try to analyze it. Okay, so that is the aspect that you come across it. The next is here. So probably all the students would have written the code using C language, sir. Probably multiplication of the matrix or addition of the matrix. So here again, the development of the code is very similar to that. Okay, so code is nothing but the set of instructions. Okay, so probably they'd have worked out the program for the addition or division or multiplication of matrix. It is very similar to that. Only thing is here, you use certain approximation solution techniques, either FDM, FEM, or FBM. So probably mechanical students do study about FDM method. They will study it in great detail about FEM. They can use even FEM to model the things here. Okay, so FEM is more appropriate or easier because all the commercial packages use FEM. So probably you have a very good book. Okay, so for the beginners with CFD, finite volume method by Bastig and Malala Shekara, you have it. That's a very good book for understanding the finite volume method. Okay, it's a very good book. So probably you have many simple codes, online codes that are available. Public domain codes are available. So they can take those codes and try to modify the codes based on the need and try to work out the problems on it. And you have many menu-driven tutorials also, sir. So probably which are available. So menu-driven tutorials, case studies, they have it. So they can try to work on these case studies and then look into it. So probably the development of the code is much more when you come across the CFD.
Thank you, sir. Thank you for learners. Very good advice. Thank you.
Okay, thank you, sir. Any other queries? So if there are no queries, can I wind up, sir?
Tulsidas sir. Hello. Basraj.
Hello. Very quickly, is it possible to customize fluent material database? A question from Shiv Prasad.
Yes, sir. Come again.
Is it possible to customize fluent material database?
Yes, sir. It is possible, sir.
Madhusan ಸರ್ಗೆ ಬಿಡುವ. ಸರ್ ಮಧುಸೂದನ್ ಸರ್ಗೆ ಹೇಳ್ಬಿಡಿ. ಥ್ಯಾಂಕ್ಸ್.
Sir, you can customize it because you come across the UDF influent. Okay, user defined function. So using the user defined function, you can customize the material base in your fluent also.
Stop ಮಾಡಕ್ಕೆ.
HOD sir, you continue.
Yes.
Okay, sir. Right. Now the time for vote of thanks. Today's speaker, Dr. Narendra Kumar sir, professor and at the Incubation Center, Jyoti Institute of Technology. When we invited him to participate in the webinar and our FDP to give a talk on CFD, he is readily accepted without second thought. And he gave a wonderful talk by focusing on basics, fundamentals, applications, and case studies, and even modeling, and the software tool required for CFD, etc. So, Narendra Kumar sir, on behalf of the institution and the team of FDP, first thing I would like to thank you, sir. Thank you very much for participating and giving wonderful talks, sir.
Thank you, sir. Thank you for giving me an opportunity, sir.
Sir, thank you, sir. And I also thank our management, principal, sir, Dr. H. Ramakrishna, sir, and our FDP main convener, Dr. Markandeya, sir, and team, and all our participants, even our SAPTHAGIRI College mechanical students. I thank everyone for joining us. Thank you, one and all.
Hello. It is note to all the participants. So the day 3 morning session closes now. So afternoon session starts at 2:30. Professor Dr. Ram Narsimha, principal, KSSEM is going to give a lecture on basics of CFD, general aspects of CFD. Then after that, Dharmendra Tripathi is going to give a lecture on fluid dynamics, not CFD. It is on fluid dynamics. So with this, we end the morning session. Thank you. Hope you have enjoyed the morning session. See you soon at 2:30 with the same meeting ID. Thank you.